How's it going? So yesterday we didn't really do anything new, but remember I talked about there's going to be a quiz tomorrow, just a 15-minute quiz. That's all we're doing in class. And then on next Wednesday, there's a test. Okay, so don't forget about those two things. So today we're going to start talking about special triangles. So there's two different types of special triangles we're going to talk about. In today's lesson, we're going to talk about isosceles right triangles. Okay, isosceles right triangles. Okay, so an isosceles right triangle looks like this, has a right angle and two 45-degree angles. So it turns out that if you know any one side of an isosceles right triangle, you can find the other two sides. Normally, with a right triangle, you would need 2 out of 3 sides. But with an isosceles right triangle, you only need 1 out of 3 sides. So given any one side of an isosceles right triangle, it's possible to find the other two sides. Actually, in several ways. On the other two sides, in 3 ways. Okay, so the first way would be just the Pythagorean theorem. Pythagorean theorem. Okay, so like for example, if I had an isosceles right triangle like this, an isosceles right triangle, and I told you that the length of one of its legs was like 5. You could find the missing sides here, no problem, right? If the question was, find the missing sides. I mean, what's this side right here? It's 5 also, right? Because it's isosceles, right? So if you know the length of one leg, you definitely know the length of the other leg. And then it's just a Pythagorean theorem problem. That's it. So you would just say 5 squared plus 5 squared equals x squared. And then just solve this equation. This is 25 plus 25, which is 50. So x is the square root of 50, which you could simplify if they asked you to write this in simplest radical form. What's the biggest perfect square that goes evenly into 50? It's not a perfect square. Perfect squares are 1, 4, 9, 16, 25, 36, 25, right? So this is 25 times 2, which is 5 radical 2, right? Simplest radical form. So that would be the length of this side. 5 radical 2. So no problem. Finding the missing sides is easy, right? If it's an isosceles right triangle. Even if they gave us an hypotenuse, like say they gave us something like this, and they said this is isosceles, And let's say they said this side over here was 4. Since it's isosceles, you could label this x, and you could also label this x, because they're the same length, right? And then you could still do the Pythagorean theorem, it would be no problem. You could just say x squared plus x squared equals 4 squared. So this is 2x squared equals 16. X squared equals 8. We divide by 2. So x is the square root of 8. And again, that's simplifiable. What's the biggest perfect square that divides evenly into 8? 4. This would be 4 times 2. So this would be 2 radical 2. So this is 2 radical 2. And this is also 2 radical 2. So do you agree it doesn't matter what these numbers were to begin with that I was given? I could always just find the missing pieces using the Pythagorean theorem, no problem. Does everyone agree? Okay. So that's the first way to do it. The second way to do it and you might be wondering, like, why do we need more than one way to do it? Well, because maybe this way is not the least amount of work, right? Maybe this isn't the most efficient way to do it. It always helps to have lots of different tools, right? Like, if all I had was a hammer, I could probably do a lot of things with a hammer, but some of them wouldn't be like very pretty or efficient, right? So it helps to have more than one tool. So the second method of doing this is you could actually use similar triangles. So we haven't really talked about similarity very much, but similar triangles are just triangles that are the same size, or same shape rather, different size. And the thing about similar figures, have proportional size. Now, what does that mean? Okay, so what that means is that their sides form a proportion. A proportion is just a fraction equals a fraction. That's what a proportion is. It's an equation of that form. Fraction equals fraction. Okay? So if we know that all isosceles, right, triangles are similar to this one, right here, if we knew the lengths of the sides of this one, we could just set up a proportion to find the lengths of the side of another one. Like, for example, let's just pick numbers. Like, for example, I'm going to pick this side to be a length of 1 and this side to be a length of 1. So if I do quick little Pythagorean theorem, I get 1 squared plus 1 squared equals c squared. This is 2 equals c squared, and c is radical 2. This side would have to be radical 2, right? So if I just memorize the lengths of that isosceles right triangle, I could just set up a proportion to find the lengths of any other isosceles right triangle. Like the example I gave up here, where the leg had a length of 5, I could do that here. Like I could say, suppose I have a similar isosceles right triangle where the side length is 5. I know this is 5. This is x now, right? I could just set up a proportion. I could say hypotenuse is to hypotenuse as leg is to leg. Does that make sense? I could set up a proportion that says hypotenuse over hypotenuse equals leg over leg. So I could have radical 2 over x equals 1 over 5, and then just cross multiply it. X equals 5 radical 2. I get the same answer that I got before, 5 radical 2, but in a much quicker way. Does that make sense? If you look up here, that's the answer we got. We got 5 radical 2. But I did a lot less work in this case. I just set up a quick little proportion between the sides of similar triangles. And the same thing goes for the other situation. Like in the other situation, I had an isosceles right triangle in which the hypotenuse was 4. So if I'm trying to find the length of that leg, same deal. I could just set up a proportion with this isosceles right triangle that I know its lengths of. Does that make sense? I could just say hypotenuse over hypotenuse equals leg over leg. 4 over radical 2 equals x over 1. Now this one's actually already solved for x, right? It's already solved for x. I have x equals 4 over radical 2. But you have to rationalize the denominator, like always. You can't leave a radical in the denominator. So I have to multiply by radical 2 over radical 2, which gives me 4 radical 2 over 2, or 2 radical 2. And that's the same answer I got up here. You look up here, that's the answer I got. I got 2 radical 2. But I did it a much different way. Instead of using the Pythagorean theorem, I set up a proportion with a similar triangle. Does that make sense? So the first way of finding the missing sides of an isosceles right triangle was the Pythagorean theorem. The second method was using similar triangles. There's a third method that's the best of all. The third method is using shortcuts. And there's really easy shortcuts that you can use to find the missing sides of an isosceles right triangle. Here are the shortcuts. If you know the length of a leg, if you know the length of a leg, one of the congruent legs, then the hypotenuse is equal to the leg times radical 2. It's that simple. The hypotenuse is equal to the leg times radical 2. So if I had an isosceles right triangle that looked like this, and they told me this was 7, this would have to be 7, and this would have to be 7 radical 2. No work required, you just know it. Or if they gave you This is 11. This would have to be 11, and this would have to be 11 radical 2. You just multiply the leg times radical 2. Now, sometimes the leg might be a little bit more complicated looking. Like, for example, they might give you something like, suppose this leg is the square root of 5. Well, then this leg would be the square root of 5 as well. And this hypotenuse would be the square root of 5 times the square root of 2, which is radical 10. You can multiply the two numbers because they're both underneath the radical. It's that simple. And you can confirm this, like using Pythagorean theorem, if you're doubtful like that this is actually true, it definitely works. Like if I take radical 5 squared plus radical 5 squared, and I'm wondering if that's equal to radical 10 squared, it definitely is. When you square a radical, it just gets rid of the radical. So this is 5 plus 5 equals 10. Yep, that's definitely true. Okay, that's the first shortcut. If you know the length of a leg, then the hypotenuse is the leg times the square root of 2. The second shortcut is if you know the length of the hypotenuse. Then, to find the length of a leg, the leg is equal to the hypotenuse divided by radical 2. Which, if you look at the first shortcut, it's really saying the same thing. You solve this equation for leg, you get leg equals hypotenuse divided by 2. Okay? So if I have a right triangle, isosceles right triangle like this, and I knew the length of the hypotenuse, right? So like, let's say the hypotenuse had a length of 12. Then this leg up here would be 12 divided by radical 2, which you then have to rationalize by multiplying top and bottom by radical 2, which simplifies to be 12 radical 2 over 2, or 6 radical 2. That's the length of each leg, 6 radical 2. There's no avoiding that rationalization process. Even if you did this by the Pythagorean theorem or by similar triangles, you'd still have to do that. So it's not like you're avoiding something that's hard by doing it one of the other ways. This is actually the best way to do it, using the shortcuts. Okay, isosceles right triangle. That's it. Let's try it. And by the way, like if I want to indicate this was isosceles, one way to do it is the way I've been doing it, which is just by marking the sides are congruent. They might do this though. I mean, that indicates that this is an isosceles triangle as well, right? If the base angles, two of the angles are congruent, it's isosceles as well. Okay, so just beware they might do that. So if I knew that this hypotenuse had a length of 8, and I'm trying to find the length of one of these legs, say x or something, then I know that x is actually equal to 8 divided by radical 2. That's it. Rationalize it. So this would be 8 radical 2 over 2, or 4 radical 2. That's the simplest radical form version of this. All right, so that's what this homework is about. They're going to give you a bunch of isosceles right triangles and ask you to find a missing side of it. They'll give you one side. of the isosceles right triangle, and you have to find a missing side of it. So if they gave you a leg like this, let's say they told you this was 15, find that. Then the answer is 15 radical 2. That's it. You just multiply the leg times radical 2. And if they gave you an isosceles right triangle like this, and they told you the length of the hypotenuse, like say this was 3, or let's do something weird like the square root of 6 or something like that. Okay, and they wanted you to find the length of a leg, then that leg would be the hypotenuse divided by radical 2, which in this case, you can divide them because they're both underneath the radical, you get radical 3. That's the answer. Okay, so if you know the leg, you multiply it by radical 2 to get the hypotenuse. If you know the hypotenuse, you divide it by radical 2 to get the leg. That's the bottom line. That's all we're doing today. Everybody understand? Want me to do any more? Okay, so this homework, like if you know these shortcuts, this homework should take you 5 minutes. Okay, it's super easy. But you got to make sure that your answer is in simplest radical form. Here, it automatically kind of is, but here, you have to do the rationalization sometimes. So just be careful. Okay, so the homework's on Delta Math. It's just called Special Triangles, 45, 45, 90. That's what it's called. Okay, I'm going to stop recording.